We've got a special guest here, Scott Sinclair, hanging out in South Carolina. He was bragging about how warm it is. And he's going to be presenting industrial noise control strategies for acoustical insulation. He's so involved in acoustical insulation that he said he can shred a mean tune on an acoustical guitar. So I'm thinking we're going to have to invite him up to Canada around a campfire at a kayak event, and he can tell us more. So welcome, Scott, and we'll put a muted, warm welcome round of applause for Scott. So kick it off, Scott. And just like always, I'll be moderating in the background. Any chats or questions, just be firing them at me, and I will jump in and present them to Scott in an appropriate time. And welcome, everyone, and we'll get rolling. Thank you.
All right, thank you very much, Sean. And as well, good morning, good afternoon, and good evening to everyone. And thank you very much for joining us for this discussion on industrial noise control. Before we get started, just a tiny little bit of housekeeping. We do need to make sure everybody is aware that the information that we'll be providing in this webinar today should not be used as a substitute for professional engineering design and or documentation that might be required by your local building codes, a contract, or any applicable law. And that we highly recommend that you refer to all and any manufacturer's specific application guides, instructions, and guarantee requirements for any project work and specification work that you might be doing. So with the legal ease out of the way, we'll go ahead and kick it off and get started. Quick overview, introduction to myself, and overview of what we'll be covering today. I am the National Specification Manager for Johns Manville Industrial. My contact information is there if anybody wants to grab it real quick, and if they want to reach out to me afterwards for additional questions. I have a bachelor's degree in electrical engineering from Virginia Tech, too many years ago for me to want to admit. Spent about the first 20 years of my working life in the semiconductor electronics field in a wide variety of different positions, from engineering and operations to product and project management. And then I decided that I needed a change and jumped over to a completely different world and joined the industrial insulation business. And I've been doing that for about the last 17 years. I have been with Johns Manville as National Specification Manager for about a year and a half now, but I have quite a good bit of experience in many different aspects of the industrial insulation segment from working with different suppliers in that business. And here's a quick overview of what we'd like to try and cover today. We'll start off with a short discussion about the basic principles of sound control. Look at some aspects of how do you influence or control sound. Take an overview of how materials are tested for materials acoustic performance. Then we'll do an overview of what is the most widely accepted acoustic standard for industrial applications, and that is the ISO 15665 standard. Take a quick look at some ISO 15665 results and how to apply those results, and then do a quick overview of looking at designing effective thermal and acoustic insulation systems, because it, especially in the industrial realm, it's rather rare for something to just get acoustically insulated. Usually it is some type of a thermal acoustic combination. So there's a couple of highlights there that we want to make sure that you're aware of. So let's start off and talk a little bit as an introduction about why sound control is necessary. One of the primary drivers behind the interest in sound control, obviously, is personnel protection, making sure that workers within a facility or people out and about living their daily lives will not be exposed to noise levels that could cause any damage or loss of hearing capability. One of the challenges that we do have is that there's a lot of variation in terms of what is considered a safe or a dangerous noise level, and an extreme amount of variability in terms of where the threshold is that different government organizations recommend for when you need to implement some type of sound control protection. OSHA, the Occupational Safety and Health Administration, limits noise exposure to a level of 90 dBA over an 8-hour work shift. However, they also then state that 85 dBA is the action level. And so that creates a little bit of confusion in and of itself. Another one of our national standard organizations, the National Institute for Occupational Safety and Health, or NIOSH, only allows a limit of 85 dBA across an 8-hour exposure period. Within the European Union, we see a limit of around 87 decibels for that same 8-hour working period. And then in some other European areas, we see limits varying from 75 dBA up to 100 dBA. So you have to be very aware of what the requirements are in your specific area to make sure that you are following any of the necessary regulations that would govern your facility. Obviously, as I mentioned, the main reason for looking at industrial insulation is safety of personnel. An excellent way to look at this is to account for the fact that when you're in your working environment, you want to make sure that the workers are able to hear not only their coworkers if they're trying to tell them something, share instructions with them, or give them a warning or an alert, but so that they can also hear any warning sirens if there's a need for an evacuation or anything. If the noise levels are too loud and people can't hear each other, workers can't hear each other, workers can't hear safety warnings, then that creates a very dangerous environment. So that tends to really drive a lot of the requirements for personnel protection. And then other regulatory agencies may have more stringent requirements than some of what we've looked at today. There's also environmental regulations that can come into play depending on where your facility is located. Looking at controlling noise in the environment. If you happen to have an industrial facility in close proximity to a residential or commercial business area, there might be restrictions limiting the noise emissions of the facility so that it doesn't disrupt any of the adjacent neighborhoods or businesses. Looking at issues like sleep disturbance or even just quality of life issues. Somebody can't sit out in their backyard because there's too much noise coming from the plant a mile down the road. In some areas, there are even regulations governing noise emissions due to the impact that noise can have on wildlife. And then there's a lot of what get referred to as, good neighbor regulations, businesses wanting to just make sure that they are in good relations with everybody in and around them because that makes everybody's life easier going forward. If you take a step down a little more in the details and start looking at things from the equipment level instead of necessarily just from the facility level, most equipment noise specifications typically state there's an 85 dBA limit at 1 meter distance away from the piece of equipment. Some of the challenges with that are that is only relative to that specific piece of equipment, and it doesn't take into account anything related to cumulative noise as a result of other pieces of equipment that may be in that same general area or within close proximity. So there's nothing relative to the sum of the noise in a particular area, just that individual piece of equipment. And there are usually no specifications specific to any auxiliary components of that piece of equipment. So no piping or structural steel or exhaust stacks or anything like that might be attached to it. They are just talking about the piece of equipment itself. And very often you will find that emergency equipment like backup power generators and things are exempt from many of the noise restrictions because they're considered essential. So with that background covered, let's take a look at some of the principles of sound control. And there's really three critical aspects or fundamental principles of noise or sound that really come into play. The first is amplitude, and amplitude is the height of a sound wave, as you see represented in the little graphic on the right-hand side. And so that's the distance from the mean of the sound wave to the peaks, either positive or negative peaks from the mean. Another very critical factor when you're looking at sound and noise reduction issues is the frequency of the sound, and that is the width of the sound wave, very often described as the number of oscillations that occur within a specified time period, and that is where you would see the hertz rating for sound, something that's 1,000 hertz, 2,000 hertz, 50 hertz. That all relates to the frequency or width of the sound. And then you'll very often see things referenced as dBA, and that is an A weighting that is applied to the decibel or dB sound level. And it is a logarithmic summing of the individual octave band sound pressure levels that is applied, and it's a weighted summing. And it's applied to the sound pressure levels at each octave based on how the human ear perceives the loudness of that frequency of sound. There's a strong relationship between the frequency and the loudness of the sound and how well the human ear perceives that frequency sound. And so very often things are given an A weighting to account for the fact that you typically will hear mid to low high frequencies better than you might low frequency sound. So when you are looking at frequency of sound or noise, that's typically broken into three classifications. The first is what you would refer to as low frequency, or what would be considered a rumble. So that's a very long wavelength, usually in the 31 to 63 hertz range. That might also be what you're very familiar with, the person playing their music in the car next to you extremely loud, and you get that bass thump that shakes everything. That's your low frequency sound coming through. Then there's the mid frequency noise. It's typically referred to or often referred to as a roar. That's usually the 125 to 500, possibly 1,000 hertz frequency range. And then you have your high frequency sound, which is often considered to be a hiss, and that is your 1,000 to 8,000 or 10,000 hertz sound. So each of these can be addressed in different ways. Each has different requirements in terms of what is necessary to reduce the amount of noise at each frequency band that you might hear. So it is important to understand how different pieces of equipment might generate noise of different frequency levels. And that's represented well by this graphic. You can see that when you get into the very low frequency sound, you're looking a lot at structure-borne vibration. So back to the thumping of music, the very low bass sound that causes things to shake or things to vibrate. When you have a train engine that passes by on the railroad tracks, you can often feel it in the ground. That's a very low frequency vibration that's occurring. Then when you start moving into pieces of equipment like what you might see in some of your industrial facilities, you're looking at coolers and pumps and motors and compressors, you're going to start getting into that mid-frequency sound, things in that 125 to 1,000, 2,000 hertz range. And then when you start getting flow related noises or hisses through valve and bypasses, or pressure controllers, flow valves, things of that nature, you're going to start getting into that high frequency noise. So I'm sure many of you can probably relate this to what you experience on a day-to-day basis in the facilities that you work with. So let's take a look at ways you can influence sound and ways you can go about controlling sound. An important piece to remember when you are looking at sound, looking at noise-related issues, people very frequently speak about what's called the source-path-receiver relationship. So in every sound-related issue, you have something that is the noise source. You have a path by which that sound must move to get from the source to the person or object that hears the noise. And then you have the receiver, the person that does hear the noise at the end. Obviously, the best way of trying to address noise, because it gives you the best control over it, is to address noise at the source and reduce the noise at the source. If you're in a situation where that is very difficult to do, then the next best option would be to try and do something in the path segment of this relationship. How can we put something between the source and the receiver such that there isn't a straight path for the noise to transfer between the two? And if that isn't possible either, then you would have to look at some type of protection at the receiver level, which would be earplugs or earmuffs or something of that nature. But when you are looking at trying to reduce noise at the source, depending on the type of noise, which goes back to what we were reviewing a second ago relative to the frequency of different noise sources, each can lead to different types of possible solutions to try to control that noise. So when you have a pump or a compressor or blower or something with a mid-frequency, you might look at acoustic blankets over that piece of equipment, possibly an enclosure around that piece of equipment, and very frequently looking at some type of a mechanical isolation, so keeping the vibration of that piece of equipment from coupling into anything else that it might be connected to, like the structural steel that it's mounted to, or possibly the piping that might be connected to it. When you're looking at piping itself, pretty much very often similar, looking at acoustic pipe lagging solutions, looking at possibly some silencers if you have some flow-related issues, and again, looking at isolation. What do you need to do to try to make sure that any noise coming from the pipe isn't transferring into the pipe supports or the pipe racks that hold the piping in the facility? Coolers and fans, very often you have to take a look at the design of the system. Do we need to change the fan blade design so that the blades themselves aren't setting up an oscillation and creating the noise? Do we need to look at variable frequency drives for these pieces of equipment to prevent oscillations from occurring? Air intakes and exhaust systems, very frequently addressed by implementing silencers, which are basically a piece of equipment that disrupts the path between source and receiver, so that the noise has to take a path that allows it to get diminished before it gets to the receiver. And then just general noise that might exist within a facility typically would be addressed with barriers or buildings or possibly some enclosures of some nature. In the industrial arena, what you would typically look at for trying to control noise or sound is going to be an acoustic insulation and lagging system that is installed around the piping. So you'll have pipes that may have a particular noise issue, whether it's flow-related noise, or possibly the pipe is picking up noise from some other structural element that's connected to it and radiating that noise. Depending on the frequency of that noise, you would need some combination of sound absorbing material and possibly high density resilient materials, maybe a mass loaded vinyl for your lower frequencies. And then, as most of you I'm sure are familiar, with most insulation systems, you would also have some type of an impermeable outer cover or cladding system to protect the insulation from the outside environment and impact damage and things of that nature, as well as weather and that. So when you start looking at trying to address industrial noise-related issues, and very commonly it is related to piping within a facility, you have to take a look at some different characteristics of how do you look at the performance of the material that you're using to try and mitigate the noise problem. And one of the characteristics that is used for rating or looking at the performance of a material is the term insertion loss. And insertion loss is basically the reduction in the amount of noise that is radiated from the inside to the outside of the pipe uh, between a situation when the pipe has no treatment applied to it and when it is fully insulated and jacketed. So you would basically measure the noise being radiated from the pipe with no treatment on it, measure it again with the full treatment installed, and then the difference between the two readings is your insertion loss, and that would typically be a rating in dBA. It would be a weighted to address how our ear perceives that noise. Another characteristic that is very often important is transmission loss. In some regards, it's similar to insertion loss, but it's basically looking at the reduction in noise as it passes through something, typically some type of a structure, a wall, a ceiling, a floor, some kind of mechanical or structural assembly. Transmission loss is very often a critical characteristic that comes into play when you're looking at trying to reduce very low frequency noise, because that often isn't controlled well through insertion loss or absorption. So again, in insertion loss, just doing a quick comparison of the two again, is a measure of the decrease in the sound power as a result of adding a treatment. Whereas transmission loss is a measure of the decrease in the sound power because of an assembly that's applied. And in both cases, the decrease in sound power actually could be due to both absorption and reflection of the noise. And again, that's going to come into play depending on the frequency of the sound that you're trying to address. Whoops, did I go the wrong way there? Or did we get a duplicate? So let's take a look when it comes to applying an acoustic insulation solution to a pipe or piece of equipment in a facility. Some of the characteristics of the materials being used that would affect its sound absorption performance or capability. When you're looking at what would be considered an open cell material, typically a fibrous material, the fiber diameter of the material is critical. The material thickness plays a huge factor. When you're looking at fiber diameter, the air cavity that is captured within the spacing between the fibers is very critical, because that is what is creating the path that the noise has to follow as it tries to flow through the insulation material, and is basically what reduces the sound level as it tries to pass through the material. Density can come into play in looking at the performance of a material, and then the methods by which the material is installed and mounted can have a significant impact on how the material performs. When you look at closed cell insulation materials, you start having to look at characteristics like the porosity. Most closed cell insulation materials have a percentage of closed cells. They're not 100% closed cell. So a 90% closed cell material will perform differently than a 50 or 20% closed cell material. Again, looking at that cell structure, again, material thickness can become a very governing factor when looking at the performance, and again, how that material is mounted and installed can have a big impact. Installation is very critical in any acoustic insulation system, because you have to look at is there a mechanism whereby the noise of the pipe, the vibration of the pipe is being transferred to the insulation system itself, and therefore not necessarily being reduced, but it could actually be accentuated. Another term that some of you might be familiar with is NRC, or noise reduction coefficient. That's very often a characteristic applied specifically to insulation materials. Look at data sheets for different materials, you'll very often see a table like this one that describes the noise reduction coefficient capability of an insulation material, looking at the sound absorption rating at different frequencies, and then applying an NRC, which is an average of the different noise reduction ratings at the individual frequencies. When you are looking at the NRC of a product and using the NRC to try and evaluate the performance of a material, it's very important to keep in mind that the NRC is a weighted average of the noise reduction performance of that material at different frequencies. And so while you may have a product like is highlighted in this table, a 1.5 inch, 8-pound mineral wool that has an excellent noise reduction coefficient of 0.95, it's important to look at its noise reduction capabilities at each individual frequency octave, because if all of your noise is at 125 hertz, that material only has a noise reduction performance of 0.13 on a scale of 0 to 1. Where 0 is no sound absorption and 1 is all full sound absorption. That 0.95 NRC rated material may not do anything for you if your problem is at 125 hertz. So very important to understand what that NRC is really telling you when it comes to looking at your noise reduction system and how you design it. We touched on these two characteristics earlier in looking at the performance that a material will give as a result of changes in its thickness versus changes in its density. And what you will typically find is that the thickness of an insulation material will have a much greater impact on its acoustic performance, its absorption coefficient performance, than density will. The chart on the left shows the four curves on the upper portion of the graph are the same density mineral wool insulation material at 4 different thicknesses, ranging from 1.5 inches, which is the blue curve, the lower of the 4, up to a 6-inch thick, which is the purple curve up at the top of the chart. And you can see that the thickness has a big difference in that low to mid frequency range. At the high frequency range, the thickness doesn't have as much of an impact because the wavelength is very short. So you don't need as much material to dampen and absorb that noise. The 2 curves at the bottom of that chart are some thin blanket insulation products. And you can see there, one, because they are very thin relative to the mineral wool product, their performance isn't as good, especially in the low frequency range. And then if you go over to the chart on the right, where we're looking at the absorption coefficient of the materials due to changes in density, the 3 upper curves are 3 different density levels of mineral wool, all at the same thickness. You have a 4-pound, a 6-pound, and an 8-pound mineral wool being compared, each of which has an NRC represented in the chart there, noise reduction coefficient. You can see that there is very little difference in the performance of each of those as a result of the changes in density. Similarly with the 2 thin blanket solutions at the bottom, being similar in density but having different characteristics in that of the mineral wool. So many times it really is the thickness driving the performance of the solution that you're looking at. So with that information in mind, we've talked a lot about different mechanisms, different terms used for describing noise. Let's take a look at the different testing methods that are there for evaluating the noise reduction performance capabilities of different materials. One of the very common ones is the ASTM C423. That is the test that is used to measure the sound absorption performance of a material. So we were talking about the absorption coefficient in the previous graphs. This is the method that defines how to do that test. Basically, there is an enclosure with a noise source inside of it, as well as a microphone. There is a fixed level of noise introduced to the room. It's allowed to reflect off all the surfaces in the room until the noise level within the room reaches a steady state. And then the noise is shut off, and the rate at which the noise level dissipates is measured. Then you put the insulation material inside the room, and that would be the material as represented by the yellow shape on the floor of the room. And you do the same test. You run the same noise level source, let it reach a steady state, turn the source off, measure the dissipation level rate as the noise dies off. And that basically, comparing the dissipation rates of the materials, is basically what tells you the sound absorption capability of that product. This is an image of one of the rooms that's used for doing that testing, a reverberation room. Shows you the different elements involved in doing the test. You see the noise source is a speaker down in the bottom corner where the walls and floor meet. And then you have the sound absorbing specimen on the floor. You have a microphone mounted on a rotating boom. And then you have a lot of elements hanging from the walls and ceiling of the room. Those are different types of diffusers. And basically what you're trying to do with those is disrupt the noise reflection paths so that you don't get what's known as standing waves that can get set up in a room, especially one that is perfectly rectangular where you have a lot of parallel noise surfaces. You can get a situation where the noise just keeps bouncing back and forth from wall to wall or ceiling to floor, and you can actually get the noise level to add as the waves pass each other as they're transmitting back and forth, and you can set up these standing waves. So you're trying to disrupt that so that you don't have that happening, and you really are just getting a measure of the material's ability to absorb the noise and dissipate the noise once the source is terminated. So it's a very important aspect of how the testing is done. So that is really a mechanism that is used for looking at the performance of the individual insulation material. Often that is very valuable information if you're looking at introducing acoustic insulation materials, possibly in a building environment or a structural environment. But when you're looking at the industrial world, there's a standard called ISO 15665 that has mentioned earlier, been very widely accepted on a global basis as the true standard for governing the way you look at acoustic insulation systems for pipes, valves, and flanges in an industrial setting. And a couple of quick highlights out of this standard. There's a couple things that the standard does. One, it defines the test method that must be utilized for measuring the acoustic performance of any type of construction. It's important to understand that you don't test elements of the insulation system individually. You have to test the system as a whole. So that would be the insulation material itself, any mass-loaded vinyl elements that might be part of it, as well as the cladding or protective jacketing system that's utilized as part of it. So you have to test the entire system. The standard only applies to acoustic insulation of cylindrical steel pipes and the piping components attached to them. And then one of the most important aspects of this is that the standard covers both the design and installation aspects of different acoustic insulation systems and the ratings that can be applied to them. But the information that's provided within the standard in terms of system configurations and construction methods are strictly to be used as examples. They're not meant to be prescriptive. So you can't necessarily just take the configuration that's described in the standard and use your materials and build that same construction and be assured that you would get the performance as defined in the standard. So when it comes to looking at the performance characteristics of the insulation systems, the standard measures and defines performance for three different, what they call classes of noise reduction, class A, B, and C, with class A being the least stringent, so the lowest amount of noise reduction, and class C being the most stringent or the highest level of noise reduction. In addition to the ISO standard, there is also a standard that was developed and defined by Shell Corporation. And in addition to the class A, B, and C in the ISO standard, Shell has developed a class D that is even more stringent than the class C. And most organizations have adopted all four classes when it comes to looking at their noise reduction requirements. So in addition to creating the four classifications of noise reduction requirements, they also break each of those down into three subcategories by pipe diameter, because the diameter of the pipe will have a big impact on not only the amount of noise that is emitted from the pipe, but also the performance of the insulation system that is being applied to try to reduce that noise level. And so they break it down into three sizes, size 1, 2, and 3, with size 1 being those pipes less than 300 millimeters in diameter, 2 being 300 to 650 millimeter, and 3 being 650 to 1 meter in diameter. And then this is the performance requirement as defined within the standard. So within this, you can see the classes on the far left. So you have your A1, A2, A3, B1, B2, B3, and C and D as follows, with the description of the sizes that go with it. And then the standard defines the minimum insertion loss that must be provided by the insulation system that you're looking to use at each of the octave bands that are defined in the table in the standard. And you can see that as you go from A to B to C to D, the amount of insertion loss performance that is required increases, which backs up what I said a moment ago in terms of class D being the most difficult. Some people get a little bit confused by the negative numbers at the lower frequencies. They're very curious as to how in the world you can have a negative insertion loss, and it is real. It's not a typographical error. It basically means that at low frequencies, you can end up with more noise after applying the noise reduction system than you had without it. And basically that comes into play as a result of the insulation system, one, creating a larger surface area, and two, the insulation system could possibly be getting excited by the low frequency vibration and noise and creating more noise than what you had without the insulation system being there. So it is real, and definitely something to keep into account when you're looking at the performance of different systems. You might reduce noise at 2000 hertz, but end up increasing noise at 125 hertz. So you need to understand if that's going to be a problem for you or not. The actual test method itself is a pipe inserted into a special room. It exits out both sides of the room through the walls. It has a noise source at one end and a noise terminator at the opposite end. And the insulation system gets installed over the pipe inside the room. You can see the different levels being applied. And then in the last picture on the far right, you can see the microphone mounted on a sweep boom. And that is how the tests the measurements are taken. So again, you don't want the microphones getting caught in a standing wave that might occur within the room, though you see those same diffusing vanes hanging from the ceiling to try to prevent it. You also see the very angled wall and ceiling shape to the room, so that you don't have direct reflection paths opposing each other. But basically within the ISO standard, you do very similar to the ASTM test. You measure the noise level with no treatment on the pipe. You measure it again with the full treatment on the pipe, and the difference between the two is your insertion loss performance. So let's take a quick look at performance results. So some of the results that can be obtained from doing this testing and looking at standards. These are examples of systems that have been designed and tested by one supplier. Again, you can't take these as necessarily being prescriptive. The results that would be demonstrated by this are only valid for the specific materials that were tested by this manufacturer. But you see representations of a Class A/B system, a Class C system, Class D system, and then the pipe size subcategory was included in each of these. So in this case, the supplier tested to the largest of the three pipe sizes, which is the most difficult to achieve, typically has the higher noise reduction level requirement. And then you see the description of the system. So in this particular case, the AB system is 2 layers of mineral wool with a layer of mass-loaded vinyl, and then an aluminum cladding, and that meets the requirements of your A or B system. Then your C3 system is the 2 layers of mineral wool with 2 layers of vinyl, 1 pound vinyl, and again, a cladding system, but in this case, it's an O2O stainless, and that meets the requirements of your A3, B3, and C3 systems. And then the most stringent system to meet the requirements of the D3 is a layer of mineral wool with a layer of mass-loaded vinyl, second layer of mineral wool, more mass-loaded vinyl, and then again the O2O stainless steel jacket. So as you get up into the higher noise reduction requirements, you can see that the complexity of the systems does get more complicated and more involved. Some things to keep in mind when you are looking at the systems. I mentioned a critical one when we were talking about the ISO standard in terms of the systems that are described are not meant to be prescriptive, that they're only relevant or specific to the individual materials that were part of that system. The Shell DEP standard, the one that creates that Class D system, states the same thing by the section highlighted here, saying the designs listed in the table are indicative and shall be verified by prior third-party testing in accordance with the clause 10. So it again stipulating that the specific materials to be used in your noise reduction system must have been tested. You really can't substitute one manufacturer's material for someone else's because you don't know that you'll get the same performance. A couple other key things to keep in mind when you're looking at selecting your acoustic system is that configurations passing a lower pipe size test can't be assumed to pass for a larger pipe size. So if you have an insulation system that was tested to meet the requirements of a B2 classification, you cannot assume that it will also meet the requirements of a B3. And likewise, a C1 would not necessarily meet the requirements of a C2. So results are not upward scalable in terms of the pipe size. And then you also need to keep in the back of your mind that engineering judgment can be used to apply these results to specific project requirements. So you can take a look at the noise reduction performance that you get out of a B3 system and make an engineering judgment to determine where you might be able to apply that system and meet the noise reduction requirements that you have. A few additional considerations, things to keep in mind when you're looking at a thermal acoustic system, and then we'll open it up to some questions. If you are using a rigid thermal insulation, so something on the nature of a foam glass, a cellular glass, perlite, calcium silicate material, when you are looking at the acoustic insulation system that you would apply over that, you need to use the diameter of the pipe plus the thermal insulation as your outside diameter when determining what pipe size ISO system you need to select. You also can take into account if there is a thermal insulation system and the thermal material that you're using does have acoustic contribution capabilities, and vice versa. If your acoustic insulation material has thermal properties, when you're looking at a combined thermal and acoustic insulation system, you can kind of do the marriage between the two, reduce the possible thickness of the combined system by taking into account the thermal performance of the acoustic system and the acoustic performance of the thermal system, and reducing the individual thicknesses of each. On cold systems, it's a little bit different world, because that is almost always a rigid insulation material, and the thermal and acoustic materials are almost always independent. You don't get much acoustic contribution out of the thermal material. It's usually a closed cell, usually has minimal acoustic contribution. You need to make sure when you're doing a combined thermal acoustic system on cold, especially cryogenic systems, that the proper vapor retarders are installed not only over the thermal insulation, but also over the outer layer of the porous or open cell acoustic insulation, so that you don't get vapor migration and condensation within the acoustic insulation system. And it's important to make sure that the acoustic material is always the outer layer of the combined thermal and acoustic system. The acoustic material would never go on the inside of the thermal insulation. And with that, that brings us to the end, and we'll open it up to any questions that anybody may have.
So Scott, Scott, it's Sean here. I'll kick off with a couple questions for you. What's the importance in the reducing your sound noise vibrations of pairing up anti-vibration hangers and supports, and potentially engineering in an anti-vibration system to your noise during design? Have you seen that growing in popularity in the last few years, or what's your take?
That's a very critical aspect of all this. And early on in the presentation, we did talk about how very when we were looking at different noise reduction solutions for different types of noise sources, you very often saw included in the table isolation as one of the elements. If you have a pipe that is acting as a noise source, that is usually because there is some type of a mechanical excitation of that pipe. So if all you do is apply an external acoustic insulation system to the outside of the pipe, the only thing you'll reduce is the noise being transmitted by the pipe. If that pipe is held in place by some type of a hanger or a pipe support of some nature, and then the hanger or the support are in direct contact with the pipe, then that vibration in the pipe is most likely going to transmit into whatever that structural support mechanism is, and possibly cause the excitation of that element, or maybe something else that support is attached to. So you may quiet the pipe, but you may create a noise source somewhere else within the structure of the system. So isolation can be as important an element as just the acoustic insulation itself.
What about products being used? Do you see lead-based products in recent history, or has that been phased out?
What based? I'm sorry.
Lead,
Well,
lead-based?
very few people use lead for much of anything anymore, because it's been banned in most countries. You saw in the configurations, ISO configurations that I talked about in the presentation, that they did include a mass-loaded vinyl. Usually, before lead got banned, lead would have been used as the mass element. Today, it is usually a barium-loaded vinyl of some nature. So they've just changed from lead to other materials that aren't a health and safety risk.
Do we have any questions coming in from the line? I think everybody's unmuted to ask, or will be unmuted. Nothing's come in through the chat line, Scott, yet.
Okay. don't be afraid to ask your questions if you have one, because if you thought of it, then probably half the rest of the audience is too, but everybody's too embarrassed to ask it. Or if you really don't like asking questions in front of all your colleagues, you have my contact information on the screen again. Feel free to reach out to me separately, but the best benefit for everybody is to ask the question now so everybody understands the answer.
We had a comment come in, Scott, that the presentation was very well covered.
Ah, thank you very much. I appreciate it. We do try very hard to really share as much information as we can about the subject when we put together these webinars, and keep it as informative as we can. So thank you. Appreciate your feedback.
Hey, just a quick question on access to the PowerPoint. Is that something that's going to be an option for us? I certainly could use another pass through all this info.
Yeah, Kelly, this is Sean here. So we have been recording this presentation, and they've typically been uploaded to our website for members to have access to post webinar. So absolutely.
Yeah, just having the PowerPoint by itself probably wouldn't be extremely effective, because a lot of the meat of the information is in what I presented with the slides, and isn't necessarily covered in the slides themselves. But having the recorded presentation will definitely give you access to the information.
Yeah, I appreciate it. I'll go online afterwards. Thank you.
Thank you. Any other questions, anybody?
Just an update from Robin. The recording will be available tomorrow.
All right, don't be shy. We're here to answer the questions you may have. I probably didn't do that good a job covering all the information.
Well, I think it was a well-detailed introduction, a lot of technical information to digest, Scott. I know in the TIAC world and our members, whether they're contractors, manufacturers, or distributors, it's becoming more apparent that people are paying attention to design and getting that involved. I know on the contracting side, there's been a lot of situations where the design of the acoustical issues hasn't been thought of until it's too late. So then they think, the engineers and the operators think a contractor can come in and solve with mass layers of insulation. But like I asked the question about supports and then hangers, because if you design it, no matter how much insulation you put on, you can't reduce that vibration or that noise that's in there. So the design has to be started.
Yeah, that raises an excellent point. Sean, thank you for saying it. Very often people like to think of acoustic insulation systems very similar to thermal insulation systems, in that, the more I put on, the better it has to be. And in the acoustic world, that can absolutely be anything from the truth. Just applying more material, whether it be insulation, mass loaded vinyl, or whatever, doesn't necessarily mean you'll reduce the noise more. You can create a condition where you actually end up with a whole lot more noise than you started with.
So just a quick question here, Scott, too. And I used to use 3E plus. I'm not sure if you're familiar with it with NIA.
Very familiar.
So was there any calculations for acoustical, or if there's not in 3E plus, is there any programs like that one could go sourcing in?
The 3E doesn't do anything with acoustics. I am not aware of any specific tools that are available for doing that. I know there are systems available or packages available in use with a lot of the CAD design programs, where you can do acoustic modeling of the system that you're designing. I don't know if that takes anything into account in terms of looking at noise reduction mechanisms, or if it's just from the design aspect, what you might expect in terms of noise levels, And then you would have to refer to something like the ISO standard and say, okay, my modeling tells me that I'm going to be at 95 dB at 2000 hertz, and therefore I need to get below 85. So I need something that's going to give me 10 dBA of insertion loss at that frequency. So that would probably be the path you'd have to take.
Yeah, and a comment came through on the chat line from Dominique and hanging out in beautiful Montreal, but he stated, all situations are very unique for each
Yep.
acoustical no same situation occurs really.
Yeah, as much science as there is in acoustics, there's also an almost equal amount of black magic in acoustics. So
Right.
it can be extremely challenging.
So a comment came in from Mark Trevors, who's probably hanging out in Edmonton. I think I saw earlier on the chat, and he said in the past he's had to install galvanized metal between the mineral fiber insulation on ID fans. He's asking, would the mass loaded vinyl be a better product? And I would assume, yeah, that would be a better product in that situation. What do you think there, Scott?
It's obviously going to depend on what configuration you're having to utilize, whether it be a class A, B, C, or D. If it is one of the systems where the vinyl is the outer layer of the system just before the jacket, mass loaded vinyl is probably going to be your best solution. It's going to give the best performance as far as the dampening and the deadening of the low to mid frequency noise. Metal, the mass of the metal can contribute, but metal is usually more easily excited than a mass loaded vinyl would be. The one area where that might be an exception to that rule is when you're looking at a class D acoustic system on a hot thermal insulation system. You may need to take into account the interface temperature between the two layers of mineral wool in the Class D system, where there is a layer of vinyl in between, and make sure that interface temperature doesn't exceed the upper temperature limit capability of the mass loaded vinyl. If it does, then you may need to substitute a metal of equivalent mass for that layer of vinyl.
Some good questions, some good conversations happening here, Scott. So right on.
Excellent, excellent. Yeah, that was a very good question.
Anything else coming out? I think we're at our time limit, so I'm guessing that's probably time to call it a great session. We've got to thank you very much coming in to Scott. Appreciate your time and sharing of information. Thanks to the innovators and everybody who kind of helped us put this together. And another thank you coming in. So I think that's probably it for the questions, Scott. If you've got a closing or if we want to just end it there, I think it's a natural spot. So thanks for everybody for carving out their time.
Yep.
Great high fives to Scott for a great presentation, and all the best, and we'll talk to you soon.
All right. Thank you, everybody. Thanks for joining us. Have a great day.